Welcome to my channel. In today's video we look at how to solve congruence equations. So let me share the working so that I show you a few examples on how to solve congruence equations. Just like in our earlier video, I look at various methods so that you see how those methods can be used in solving congruence equations. So what I said, let me just write the subject of our class today, and we say that we are finding solutions to congruence equations. So we find solutions to congruence equations. Now, so I'll begin with the first example, and the example is solve. I want us to solve for x is congruent to 3 mod 9. 3 mod 9. Now, so by a solution to this equation, what we want is the value of x. So that 4 times x gives us 3. And recall that this 3 is the remainder when the value here is divided by 9. So the remainder is 3. So we want a number which, when multiplied by 4, the answer that we get, if we divide it by 9, the remainder will be 3. Now, this is a very easy question because the module here is relatively small. If the module is relatively small the way it is, we can use trial. We try all the numbers of mod 9. So mod 9 will mean numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. So when the module is relatively small, this 9 for example, then we try all these numbers and we see which ones, if multiplied by 4 and then the solution divided by 9, the remainder will be 3. But as we proceed, this is not the method I'll be using. I'm just using this method because the module is relatively small. But of course, we have other methods. As I look at them later, we'll be using the extended Euclid's algorithm. We can also use the Fermat's little theorem to get the inverse of 4 and multiply by that inverse on both sides. Or we can also use the Euler theorem to find the inverse of 4 and multiply by that inverse on both sides. And you know, when you multiply 4 by its inverse, you get 1. So the left side will be left with the x, and that is what we are looking for. And then you multiply by that inverse here, and so you have the solution. But let's use this trial first. So what I mean is you try 0 times 4 and see whether the remainder will be 3. So we find that the answer will be 0. And therefore, this 0 is not congruent to 3 mod 9. Let's see, what about 1? 1 times 4 is just 4. And 4 is not the same as, is not congruent to 3 mod 9. What about 2? So we just try. What about 2? Because we have a very small module, so we can try all the values. What about 2? So 2 times that will be 8. And 8 is not congruent to 3 mod 9. It's not the same as this. What about 3? 3 times 4 is 12. 12 divided by 9. 9 goes into 12. 9 goes into 12 once. And that you get 9. 9 from this 12, the answer will be 3. So the remainder is 3. The remainder is 3. If 9 goes into 12 once, and so the remainder is 3. And that's what we wanted. So this is congruent to 3 mod 9. What about 4? 4 times 4 is 16. 9 into 16, the remainder will be 7. And 7 is not congruent to 3 mod 9. What about 5? This will be 20. 9 into 20, the remainder will be 2. And 2 is not congruent to 3 mod 9. And then 6, that will be 24. 9 into 24, it will go there twice because of 18. And so the remainder will be 6. The remainder will be 6. And 6 is not congruent to, it's not 3 actually, it's not congruent to 3 mod 9. And then 7, that will be 28. 9 into 28, you have, it goes there thrice because of 27. So the remainder is 1, which is not congruent to 3 mod 9. And then we also have 8, that's the last value. 4 times 8, and that will be 32. 9 into 32, it will go there 3 times because of 27, and the remainder will be 5. 5 is not congruent to 3 mod 9. So we've discovered that the only solution to this congruence equation is this 3. It's 3. So x is 3. If you want, you can write it 3 mod 9. So we've discovered that it's only 3 multiplied by 4 that will give you 12. So that's 12 divided by 9, the remainder will be 3. What is written here is always the remainder. So the remainder is 3. Now, this example tells us one good thing here. We discovered that the GCD between 4 and 9 was 1. So the GCD is 1, and that one divides this number here. Supposing the GCD is A, let me just say, suppose the GCD is A. Supposing the GCD of two numbers, let me use C and D. Supposing the GCD of two numbers C and D, where I have something like this, Cx is congruent to E mod D. So I'll get the GCD of C and D. If that GCD is A, I will check to see if this A would divide this remainder. If that GCD divides this remainder, it means this congruence has solutions or has a solution. So how many solutions? The solutions will be equal to the GCD. So if the GCD is 1, then and that 1 divides this number, then this system or this congruence has one solution. If the GCD is 2, and supposing 2 divides this number E, and then this congruence would have 2 solutions. And so that is how we will be doing our work. Now, so supposing this, when I began, I said that this module was relatively small, and therefore I used this method, and I found the answer is 3. And I also stated that I'm not using that method because in some cases I'm given a module which is large. Module could be large. So now let me show you how I would have done it without this trial and error. And so if I was to do it now using the other method that I would use the extended Euclid's algorithm, or I can also use the Fermat's little theorem to find the inverse of the number here, or the Euler theorem to find the inverse of this. And in our previous video, we looked at how to find the inverses. We use Euclid's algorithm. Or you can call it extended Euclid's algorithm. I want to find the solution to this if it exists. The first thing I'll do is to find the GCD of 4 and 9, and I've seen that it's 1, and 1 divides the remainder, is 3, and this therefore means then this congruence here has a solution, has one solution. Remember I said that if the GCD divides the remainder, then the number of solutions will be equal to the GCD. So since the GCD is 1, this congruence has only one solution. Let's find the solution. So we use the Euclid's extended algorithm. I ask myself, how many times does 4 go into 9? And the solution is 2, and then the remainder is 1. So what about for 1 into 4? 1 into 4 to be together 4 times. But this is not important. What is just important is this, that this is the GCD. You already have the GCD here. So we now make the GCD the subject of the formula. Make the GCD the subject. The GCD is 1, which equals to 9 minus 2 multiplied by 4. Now, in our previous video, at this point we stated that this -2 would be the inverse of 4. I'll come back to that, but let me call this equation star. Now, what we wanted was 3 equals to something times 4 plus 9 times something b, so that this 4, this r that is multiplied by 4 becomes the solution. This is what we wanted, but this is what we have. So to get a 3 here, I only need to multiply star by 3. Multiply star by 3. So if I multiply star by 3, then what do I have? 3 is equal to this one. You can write a 1 here, it's no problem. So we can say that is 3 now times 9 minus 3 times this would be 6, 4. So this is what I wanted, that the A here will be the solution we are looking for. That means that the solution therefore x is -6 mod 9. -6 mod 9 is the solution. But it's always good to have this. So this remainder here, this is the remainder. This remainder is always good to make it positive. If I was to make it positive, then if 9 were to go into negative 6, the remainder would be 3. If 9 was to go negative 6, the remainder would be 3. So that, yeah, you know how to divide it, and it will go to negative 1. Negative 1 times that will be negative 9. When you subtract this from that, the remainder will be 3. The remainder is always positive. So this is what we are looking for. So that is the x we are looking for. That's the x. And that is the solution to this. So that x times 4 gives you 12. And when I divide 12 by 9, the remainder will be 3. That is one way you can use Euclid's algorithm. The other way you can use Euclid's algorithm, you have to do it up to where I've written star. So from star, or from that star, from equation star, we notice that the inverse of 4, the inverse of 4 mod 9 is negative 2. The inverse of 4 mod 9 is, let me just erase this first. The inverse of 4 mod 9 is negative 2 mod 9. Negative 2 mod 9. Of course, these are remainders, so we can write it in positive, as positive. And so negative 2 is the same as 7 mod 9. 7 mod 9. So that is the inverse. So once you have the inverse, I said you begin from here and then you come up to star. So that means if you're using this method of inverse, you don't require this other one. You don't require this other one. So you just from star you come to this straight away. And once you have the inverse, go back to the equation and multiply both sides by the inverse. So then you would have 7 multiplied by 4x is congruent to 7 multiplied by 3 mod 9. This is an element times its inverse, that gives you 1 times x, that will be x. And this is 21. 21 divided by 9, what we need here is the remainder. 21 divided by 9, 9 will go there twice because of 18. So 18 from 21, the remainder is 3. And so this is the solution. Again, we use Euclid's algorithm. So you can decide to use the earlier one, where you come up to here. Or from here, from star, you can proceed this way and try to answer that. That is how we do by Euclid's algorithm. I now want to do the same question using Fermat's Euclid theorem. Now to use Fermat's Euclid theorem, remember that I have to look at this, because what I want is the inverse of this. And we say that to get the inverse of this, using Fermat's Euclid theorem, then I have to look at moduli here. The moduli here must be prime. The moduli here must be prime. And it must be such that it does not divide this 4. It must be such that it does not divide this 4. So, but 9 is not prime, so that means Fermat's Euclid theorem cannot work. Fermat's Euclid theorem cannot work because 9 is not prime. So the only one I can use now is I can use Euler theorem. I can use Euler theorem. That is the other method I can use. Instead of this Euclid's algorithm, I can use Euler theorem. So Euler theorem, I can only use it to get the inverse. And then once I get the inverse, I proceed the way I've done the other one. Let me just find the inverse here first, and then I show you how to proceed. So using Euler theorem, to find the inverse of 4 mod 9. Euler theorem can be found because Euler theorem, the only condition is that the module here, this number 9 and this number 4, their GCD should be 1. If their GCD is 1, then, and if they are both positive, then we can find the inverse of this number. We can find the inverse of 4. And so the inverse of 4, and you can check in our earlier video where we find the inverse, will be given by 4 raised to 5 of 9 minus 1 mod 9. Now what is 5 of 9? What is 5 of 9? 5 of 9 would be the only prime number that divides 9 is 3. So 5 of 9 would be 1 minus a third multiplied by 9, which is 2 out of 3 times 9, which is 6. So that means the inverse of 4, would be 4 raised to 6 minus 1, which is 5, mod 9. Now this is a very small number. This is a very small number, so we can just take 4 and then raise it to 5. Take 4, raise it to 5. Okay, using a calculator, just do that. And then after doing that, 4 raised to 5, divide your answer by 9 and write the remainder. Divide your answer here by 9 and write the remainder. And when you do that, you find the remainder to be 7. So that means 7 is the inverse of 4. 7 is the inverse of 4. And so after finding the inverse of 4 to be 7, what do? You proceed like this. You proceed like this. Then you now take this inverse multiplied by 4x congruent to the inverse times 3 mod 9. You proceed and find your answer to be 3. Okay, I want us to look at another example. First of all, let me erase erase the space so that we have some space to do the other example. Example 2, I want us to solve the congruence 7x is congruent to 11 mod 19. I'll begin by using the Euclid's extended Euclid's algorithm for solution. First, before I do that, I want to see if I have a solution to this system. So I find the GCD of 7 and 19 and see if that GCD can divide 11. Of course, this GCD is 1 and 1 divides 11, and so this the congruence has a solution. The congruence has just one solution because the GCD is 1. It just has one solution. Now, so we have we can now proceed and find a solution to this. Otherwise, we would have stopped at this point. If the GCD would not have divided 11, would have said the system has no solution, and we end our working at that point. Now, so let's use the Euclid's algorithm. Let's use the extended Euclid's algorithm. So by this extended Euclid's algorithm, so I want 19 divided by 7, and of course 7 will divide it twice because of 14. The remainder will be 5. And then 5 into 7 will be 1, and the remainder will be 2. And then 2 into 5 will be twice, and the remainder will be 1. So that is enough. Now let's reverse these questions. Let's reverse those and make this GCP the subject. So if I make this is the subject, 1 from this bottom equation is 5 minus 2 multiplied by 2, which is equals to 5. So I move to the upper equation and substitute 2. 2 is what? 2 is 7 minus 1 multiplied by 5. So when I do this, let's just open the brackets here. I have negative 2 multiplied by 7. Then this negative 2 times this negative 1 gives me negative positive 2. Positive 2 plus this 1 is positive 3 multiplied by 5. Move to the upper equation, the first equation, and substitute the value 5. This will be negative 2 multiplied by 7. Remember the negative here. Then plus 3. Instead of 5, it is 19 minus 2 multiplied by 7. Good. Open that bracket. This is 3. 3 times 19. And then this 3 times negative 2 will be negative 6. Negative 6 plus negative 2 will be negative 8. Multiplied by 7. So this is equals to 1. This is equals to 1. But what we want is 11 here. What we want is something like this. What we want is 11 equals to 7a plus 19b, so that a becomes our solution. But what we have instead? What we have instead is 1 is 13. It's not 13. It's a minute. It's 3. That is 3 not 13. So what we have is 3 multiplied by 19 minus 8 multiplied by 7. This is our equation star. Let me call it star because we'll use it later in some other way of doing this question. Now, so what we want is 11. So we multiply this equation by 11. So what we multiply by 11 would get 11 is equals to, this times 11 will be 33, 19, and this by 11 will be 88, 7. So that means our A, which is supposed to be solution, is the solution there, therefore is negative 88 mod 19 mod 19. But this is negative, so you can write it in positive. You ask yourself, 19 goes into negative 88 how many times? And if 19 was to go negative 88, that would be, it will go there 7 times. No, the remainder will be 7 times. The remainder will be 7, not 19. The remainder will be that. So what I did was just simple division. Just simple division. 19 into negative 88. This simple division. 19 will go here negative 5 times. So that negative 5 times this will be negative 95. When I subtract the negative 95 from that, the answer is 7. And that is the 7 I've written there. Okay, so that's how we use Euclid's algorithm. So we use Euclid's algorithm. But or if you want from star, you can avoid this other method, these other things from star. Or if you want from star, you may want to find the inverse, because this is the equation that gives the inverse. From star, you can have the inverse of 7 as negative 8. The inverse of 7 mod 19, you can have it as negative 8 mod. Once you have this inverse, go back to this equation here. Go back to this equation and multiply by the inverse on both sides. Multiply by the inverse on both sides. Mod 19. 11 times 7, these are the inverses. 7 times its inverse, that gives you 1. 1 times x will be x. And this is 121. So we ask ourselves, if 19 were to go into 121, what would be the remainder? What would be the remainder? And you find that the remainder would be 7. So just do it. Just take 121 divided by 19 and write the remainder. It's what we are looking for here. Now, good. So I've used extended Euclid's algorithm. I can also use another method, the Fermat's little theorem, to find the inverse, and proceed as I've done here. Proceed as I've done here. Or use Euler theorem and to find the inverse of 7 and proceed as I've done here. So let's just do one. Let's just do one, because you already know how to find those inverses using either Fermat's little theorem or using the Euler theorem. You already know how to find the inverses. And so after finding the inverse, you just proceed as I've shown you here. Now, if you don't know how to find the inverses using the Fermat's little theorem, how to find the inverse using the Euler theorem, then you can check my video on how I found modular inverses. Modular multiplicative inverses. Now, again, if you were to use Fermat's theorem, you would begin like this. You just begin like this. Find the GCD, see whether that GCD divides 11. And if it divides 11, then you say it has a solution and you proceed. But now I want to use Fermat's little theorem. And Fermat's little theorem, you have to check whether this is prime. And if it's prime, check that it's not dividing 7, that it cannot divide 7. And if those two conditions are met, then you can use it. You can use Fermat's little theorem. So in this case, the conditions are met. So let's find the inverse of 7. Find the inverse of 7 mod 19. 19 is prime. So the inverse of it is prime, so you can use Fermat's little theorem, and therefore it will be 7 raised to 19 minus 2, which is 17 mod Let's subtract 2. Now, so how do you find this? That one you can do it. So that's what the one I want. That's what I want to do. I'm just checking if I've written the exact thing here. Yeah, I think it's correct. Because Fermat theorem says that if A is positive and P is prime, such that P does not divide A, then the inverse of A will be given by A raised to P minus 1. No, P minus 2. P minus 2. Now, so let's do it now. So this one is bigger, so we should form squares. Let's try and form squares. Form squares. 7 raised to 1 will be 7. 7 raised to 2 will be 49. What I'm writing is a remainder. It's mod 19. So this is 7 raised to 2 is 49. 49 divided by 19, the remainder will be 11. Just check. What about 7 cubed? 7 raised to 4 will be 11 square, which is 121. Divided by 19, the remainder will be 7. And then 7 raised to 8. I'm just square this. It will be 7 square, which is 49. Divided by 19, the remainder will be 11. The remainder will be 11. Then when I square this, 7 raised to 16, which is 11 square, divided by 19, the remainder will be 7. So I'm looking for the inverse. So the inverse, therefore, which was 7 raised to 17, would be 7 raised to 16 plus 1. But 7 raised, which is 7 raised to 16 times 7 raised to 1. But 7 raised to 16 is 7. 7 raised to 1 is also 7. Mod 19. So this is 49. So if 19 were to go into 49, the remainder would be 11. So that the inverse of 7 will be 11 mod 19. And so after finding the inverse, you proceed like this. Because now we have the inverse. We proceed from here. Okay, now let's look at a Euler theorem. Now, to use Euler theorem, we only need to find the inverse, just the same way we've done for Fermat. Find the inverse and proceed the same way. So the question was me just write the question because I can see it as it's appeared here. So it was 7x is congruent to 11 mod 9, 19. So for me to do this using Euler theorem, I would first of all check if this number and this 7 have GCD of 1. If they have a GCD of 1, then I can proceed and find the inverse of 7. And so the inverse of 7 will be given by 7 raised to 5 of 19 minus 1. Since 19 is prime, 5 of 19 is 18. 18 minus 1 will be 17. So this is raised to 17 mod 19. So this is the inverse. This is the inverse of 7. And when we did, we found the same for Fermat's little theorem. We found the same. And when we did that, we found that this inverse was 11. We found it to be 11 mod 19. So when you have this 11, proceed now. Take this 11 multiplied by 7x, and that will be equal to or congruent to 11 mod 19. The left side gives you x congruent to this 121. When you divide by 19, the remainder will be 7. And that is how we use the three methods. That's how you can use either Euclid's algorithm, or if you want Fermat's little theorem, or if you want the Euler theorem. We want to look at another example, slightly different from the ones we've looked at. And so the example here is solve. So this is example 3. Solve 6x congruent to 7 mod 9. So I want to do this solution. First, I find the GCD of 6 and 9, and this is 3. And discover that 3 does not divide 7, and therefore this congruence has no solution. The congruence has no solution. You can see this question is slightly different from the ones we've done before, but I'm just emphasizing the point I stated at the beginning. I said that we'll first of all check if the GCD of these two numbers divides this. That's the time we can proceed. Now, so that means that our answer ends there. So let's look at example 4. Example 4, I want us to solve 18x congruent to 15 mod 57. And I'll show you how to use the three methods. Of course, the other two methods, Fermat's and Euler, we only look at how to find the inverse. Then after finding the inverse, we proceed. Solution. The GCD of 18 and 57 is 3. This GCD is 3. Because 3 will go here 9 times. No, 3 will go into 18 6 times. And 3 will go here. Is it 17 or 19 times? 19 times. And this 3 divides 15. And 3 divides 15. And so, the congruence has 3 solutions. Congruence has 3 solutions. And that's what we said from the start. We said that if the GCD divides the remainder here, then the number of solutions will be the same as the GCD. That's what we said. So this GCD has 3 solutions. But you cannot solve it the way it is. You must first of all reduce it. Divide it by 3, because 3 is a common factor to all these numbers. All the 3 numbers. So divide by 3. Divide the whole equation. The whole equation by 3. To get, when you divide by 3, you get 6x is congruent to 5 mod 19. Now, this is what we will solve. This is what we will solve, and then use the solutions. The same solutions will be applied to this. So let's solve this by Euclid's. First, let me use Euclid's. Extended Euclid's algorithm. Extended Euclid's algorithm or Euclidean algorithm. Now, so 19 here can be divided by 6 3 times, and the remainder will be 1. The GCD is 1, so we can reverse this and say 1 equals to 19, of course multiplied by 1, because 19 times 1 minus 3 times 6. Let me call this one double star. We call this one double star. But what do we want from star? From star, what we wanted, from star we wanted to have something like 5 equals to 6a plus 19b, where a would then be the solution. So we just multiply this double star by 5 to have what we want. And multiply double star, multiply, this is L, multiply double star by 5. So when you multiply by 5, then you would have 5 equals to 5 multiplied by 19 minus 15 multiplied by 6. In other words, the solution or the answer to the question is negative 15 mod star has mod 19. But this is negative. Let's make it positive. This would be 4 mod 19. So that means our first answer x1 is 4. X1 is 4. So to find x2 and x3, because we say that this congruence has 3 solutions. To find x2, you take x1 plus the moduli, and the moduli is 19. And then to get x3, take x2 plus the moduli, which is 19. So what does this give us? 4 plus 19 is 23. 23 plus 19 is 42. So the solutions to the earlier system, the 3 solutions we wanted to look for are therefore 4, 23, and 42 are the solutions to the original system, to this original. So you check each one of them. If you have 4 times 18, the answer that you get divided by 57, will the remainder be 15? So you check each one of them. You can even check this, check that, and you will find that these are the solutions, the 3 solutions. Now remember that by Euclid, we've been doing this question in 2 ways. I've been showing you that you can reach here at double star. You can reach at double star and proceed this way. Or alternatively, you can reach at double star and identify the inverse of 6 as -3. Identify the inverse of 6 as -3 mod 19. And this -3, you can write it in positive as 16 mod 19. And then this 16 multiplied by star. So when you multiply it by star, what do you get? When you multiply by star, multiply 16 by 6x, you get x. Multiply 16 by 5, you get 80. 19 into 5, what will be the remainder? The remainder will be 4. Because what is 19 times 19 into 5 into, what was that? This was 16. 16 of that would be 80. 19 into 80, I think it would be to go there 4 times because of 76. Yeah, to go there 4 times because of 76. So 76 from 80, the remainder is 4. So 4 here is the inverse of 6, and it's our x1 that we wanted. It's our x1. So then proceed and get x2 this way. Then get x3 now that you have x1. Because x1 was just a solution, the value of x here, the value of x here, the value of x here, and we found it's 4. We call it x1, the value of x here. Earlier on, we had found it to be 4. And now using this other method, you again found it as 4. So once you find it as 4, proceed to find x1 and then x2. Now I'll not go through the details of Fermat's little theorem and the other Euler theorem, because we've already seen how to do it. You only need to come up to this point. You only need to come up to this point and then find the inverse of 6. Find the inverse of 6. Using the Euclid's algorithm, I found the inverse of this 6 to be this 4. I found it to be 4. Using Euler extended using the Euclid's extended algorithm, I found the inverse of 6 to be 4. So you can even want to use Fermat to find the inverse. But once you find the inverse as 4, what was the inverse actually? It was 16, not 4. 16. Once you find the inverse as 16, multiply that inverse on both sides of this equation. So if I were to use Fermat, I would find the inverse of 6 as 6 raised to 17. 6 raised to 17 mod 9 mod 19. And then form the table, the square table. Ask yourself, 6 raised to 1 is what? 6 raised to 2 is that 6. What is that 6 divided by 19? What would be the remainder? And so on. And then after finding, in fact, let me show you this because I want to bring in some trick here. that 6 raised to 2 will be 36. It will be 36. And 36 divided by 19, the remainder will be 17. The remainder will be 17. But since 17 is very close to 19, why can't I just write it as negative 2? Because this was the positive. I can also write it in negative, in terms of negative, and it will be negative 2. What about 6 raised to 4? 6 raised to 4 will be 6 square raised to 2, which is negative 2 square. That would be 4. 6 raised to 8 would be this square, which is 16. But 16 is very close to 19. Why can't I just write as negative 3? And then 6 raised to 16 will be this square, which is just 9. And so, what do I want? I want 6 raised to 17. So 6 raised to 17 would then be 6 raised to 16 plus 1, which is 6 raised to 16 times 6 raised to 1. But 6 raised to 16 is what? Is 9. 6 raised to 1 is 6. That is 54 mod 19. So I ask myself, if 19 was to go into 54, what would be the remainder? If 19 was to go into 54, the remainder would be 16. So this 16 is the inverse of 6. It's the inverse of 6. And that's what we found here. So after finding that inverse as 16, you proceed the same way you proceeded at this point. Then you multiply by 16 on both sides. 16 times 6x gives you x. And then 16 times 5 will give you 80. 80 divided by 19, you write the remainder there, the remainder will be 4. And so I call that x to be x1. Then I proceed and get x2 and x3 as I did here. And the Euler phi again, you just want to get the inverse. And you proceed in the same one. Euler phi, you just show you how to find the inverse. But you already know how to find the inverse. I don't know why I'm repeating all these things. I don't think I should continue repeating because you already know how to find the inverse. And if you don't know, you already have another video to watch. One that I already showed how to find the inverse of this kind of things. Now, so what would be the inverse of 6 using the Euler theorem? It would be 6 raised to 5 over 19 minus 1. But 5 over 19 is 18. 18 minus 1. So this is 6 raised to 17. The same thing we've done. So we proceed by forming a square table. I want to look at another example. That this will be the last example. So I want to find x such that 24x is congruent to 16 mod 64. Solution. First, find the GCD. The GCD of 24 and 16 and 64 is 8. And 8 divides 16. 8 divides 16. And therefore, this congruence has 8 solutions. And so, the congruence has 8 solutions. So since the GCD is 8, let's divide that equation by 8. So divide the equation by 8, the whole equation by 8. And going to get, when you divide the whole equation by 8, you get 3x is congruent to 2 mod 8. So now we can use the Euclid's algorithm or the Euler theorem. Of course, the Fermat cannot be used to solve this. Cannot be used to solve this star because 8 here is not prime. This 8 is not prime. So Fermat's Euclid theorem cannot be used. But we can use the Euclid's algorithm or the Euler theorem. Let's use the Euclid's first of all. So 3 into 8 will be twice, and the remainder will be 2. And 2 into 3 will be once, and the remainder will be 1. So reversing this, I have 1 equals. So you know how to reverse, and you can do that. When you reverse, you get negative 1 multiplied by 8 plus 3 multiplied by 3. When you reverse this one you can do it later, and you see that you get this. Now once you have this, what we wanted was, but we wanted something like 2 is 3a plus 8b, where a here is the solution to this to star, where a will be the solution. So when I multiply this by 2, therefore I would have what I want. So multiply double star. We call this one double star. Multiply double star by 2. And when you do that, you have 2 equals to negative 2 multiplied by 8 plus 6 multiplied by 3. And so our x1 therefore is this 6. That is our x1, is 6. So to find x2, take 6 plus 8. This is modulo 8. And that gives you 14. x2, 3 will be 14 plus 8. x4 would be 22 plus 8. x5 would be 30 plus 8. x6 would be 38 plus 8. x7, what is this? It's supposed to be 46. When I add 8, yeah, it will be 46. x7 will be 46 plus 8. Which is what? 54. And then x8 would be 54 plus 8, which is 62. So these are the 8 solutions. The first solution, the second, third, fourth, fifth, sixth, eighth, no, seventh, and then 8th. Good. That's how you use Euclid's algorithm. Otherwise, I don't want to continue repeating it, but that from here you may have wanted to not to proceed this way. That you may have wanted first of all to find the inverse of 3, and the inverse of 3 would be 3. So 3 times the whole of this, 3 times 3x will give you x. Let's call it x1. And 3 times this 2 give you 6. So x1 will be 6. Then you proceed and get x2, x3, x4, 5, 6, 7, 8. So that is if you arrive at this point and want to use the knowledge of the universe. So if you want to use the knowledge of the universe, then the inverse of 3 is 3. And so this 3 multiplied by this 3, x gives you x. Call it x1. And that 3 multiplied by this 2 gives you 6. So x1 is 6, and then you proceed and get x2 and so on. Now, so let me look at the equation that we have. This is the equation. We already said that Fermat's little theorem cannot be used, but the Euler theorem can be used because 8 and 3 have a GCD of 1. So we can use the Euler theorem to find the inverse of 3 if you don't want to use the Euclid's. Extend the Euclid's up to here. You can use the Euler theorem to find the inverse of 3. So what would be the inverse of 3 using the Euler theorem? It will be 3 raised to 5 of 8 minus 1. 5 of 8 minus 1. So you only need to know how to find 5 of 8. And 5 of 8 is just 4. So what we're talking about here is 3 raised to 3. Is the inverse. 3 raised to 3 is the inverse of 3. 3 raised to 3 is just 27. 27, 8 goes there how many times? What is the remainder? So the remainder is just the remainder is 3. 8 goes here 3 times because of 24. 24 from 27, you have 3 as the remainder. So once you have this remainder, and this becomes the inverse of 3, multiply this inverse here, get x and call it x1, and then multiply this 3 by this, get 6, and so x1 is 6, and then you proceed and get x2, x3, and so on. So that is how we solve congruence equations, and we've seen how to do that using extended Euclid's algorithm, how to do that using Fermat's little theorem, and how to do that using Euler theorem. In the next video, we'll be looking at other lessons. Remember to subscribe so that whenever I upload a lesson, you can automatically